Hey guys, welcome to
Another nice superpower of the Wronskian is that if you have one solution figured out, you know this, you can find the other solution. And this is really important because the first solution for a differential equation of the form that we've been working with for this entire video is pretty it's not hard to find one solution to the homogeneous differential equation. You can, in physics or even in like mechanics, you usually do an ansatz or like an educated guess, which involves using the exponential function, because that's sort of the eigen function for this operator. See, now we're connecting to linear algebra like before. It's all connected. As long as you see the bigger picture, it's more useful. It makes you better at explaining and a better mathematician in general. Okay, so if you can find one solution by hook or by crook, again, as I said, involving exponentials or like other types of black magic. So again, this encompasses all hook or by crook. Then you can find the other solution, y2 of x. So how do we do that is you consider, say, y2 of x and y1, and you like differentiate this with respect to x, so that now you have to use the quotient rule on this guy. So you have y1 of x, y2 prime of x minus y2 of x, y1 prime of x divided by y1 of x, the whole thing squared. This is just the quotient rule from simple differential calculus. Now notice the top guy is simply the Wronskian over y1 of x, the whole thing squared. And what if we just integrate by dx with respect to x on like both sides? So we just have this differential of y1 over y2 and then integral of this here. And after evaluating this integral, we have y1 over y2 is equal to this guy, Wronskian over y1 of x squared dx, plus some constant of integration, again you have to account for. And now, let's call this c0 maybe. If I multiply both sides by, say, y2, because I'm sorry, there should be y2 here and y1 down. Messed up the order. So if we multiply both sides by like y1, because we know y1, we get y1 times this integrated junk plus c0 times y1. So y2 is this quantity plus some constant times y1. But this part is the dependent part, is the linearly dependent part, right? Because we are expressing this as a linear combination, as a scalar multiple of the y1. This is the dependent part, and this part, it has no dependence on y1, because like this integrated quantity, it may or may not be a constant. So, and if it is a constant, then it's y2 is always going to be linearly dependent. So there's just, this is the independent part, the linearly independent part, which gives like something new, which doesn't really depend on y1 in the linear sense. So we usually really care about the independent part because we can always generate a dependent part, and that will always be a solution for a differential equation. So we can sort of write this as y1 of x integral Wronskian of x over y1 of x whole thing squared dx. And the beauty of this is the Wronskian can be found out just from the form of this differential equation by the formula I talked about on the previous page. So yeah, you plug that in to this, and you assuming you know y1, you can get y2. So yep, see, this is the power. This is the power. You get one solution, you get the other, just by virtue of the Wronskian, which doesn't really, it's just a number, it's just a quantity which has these nice properties. Okay, now I would like to do an important example. This differential equation that I recently encountered while I was doing some mathematical physics. How do I solve this? Well, what we can do is we can try Frobenius. That's what we did last video. So for that, y is of the form sum from n equals 0 to infinity c sub n x to the n plus s. So we can plug that in and notice we have sum from n equals 0 to infinity n plus s minus 1 x to the n plus s minus 1 plus sum from n equals 0 to infinity n plus s x to the n plus s minus 1 equals 0. Notice both the powers are not different, they're the same, so there's no trailing term, so we can't really expand like for individual indices. So we have no choice but to club them together. If you club them together, you have n plus s, the whole thing squared, x to the n plus s minus 1 equals 0. So you notice we don't really have a generating term here. Sorry, we don't really have an indicial equation here, because there was no trailing power. We couldn't really expand for or take out some indices from the summation. There's only this generating term, and if we want this to be true for all x, we will see that like s has to be negative n, which doesn't really like say much because like n is varying, so you have s is a constant, it has to be fixed on one n. Because if you like try to sub this in here, s equals negative n, you just have cn, which is like an infinite sum of these coefficients cn, which assuming it converges. Now see, this is really important. You have an infinite series, we would assume, we can't really like just assume, we need to like really have convergence. We can't really say that it will always have some value. It should converge. That's the issue with these infinite series. Assume it converges, like y will just be a constant, like it's just one constant. You can also try another method which is called the Cauchy Euler approach. I didn't cover this because it was, I don't know, didn't really seem appealing to me back then. Now the Cauchy Euler approach is like quite similar to Frobenius solution. It says that use this guess. Now these guesses are what we call Ansatz, German term. Y equals x to the m. If we do that, we have m times m minus 1 x to the m minus 1 plus m times x to the m minus 1. Nothing different from what we had before, which means m squared x to the m minus 1 should be 0, which means that if you want this to be true for all x, m has to be 0. And again, this translates to like y being 1, x to the 0 is 1. So, well, we aren't getting much. I mean, finding or like some constant or even 1, which is again a constant, is not really like that helpful for this difference. It doesn't really tell us much about this system. So in which case, assuming you call this y1 of x, the first solution we can find the Wronskian of this system. We can use the Wronskian approach. So for the Wronskian approach, notice that we need 1 here instead of, we have an x, so we need to divide by x on both sides, so that we have d second y over dx squared plus 1 over x dy over dx equals 0. And then we are assuming that x is not equal to 0, which allowed us to like sort of divide. And this makes sense because if x were 0, this would just be a first order differential equation. Dy over dx is equal to 0, which means y is linear. So this is a valid assumption. And so we can find the Wronskian now. If you remember, the formula is some constant, w naught e to the negative dx, and p of x is 1 over x. So omega naught, w naught e to the negative natural log of x, which just becomes W naught over X. That's the Wronskian. And now we know y1, we can find y2 with the formula we found. y1 of X integral of the Wronskian, which is W naught over X times y1 squared, which is 1 squared in this case. If we use using the Cauchy Euler solution, dx. This is the independent. We want to generate the independent. No point generating the dependent because it will just be another constant, and this it's not anything different than what Frobenius solution was telling us anyways, assuming the sequence converged, the series converged. So well, y1 is 1, and if you try to solve this, you just get with some constant W naught times natural log of X, and which is indeed a valid solution for this differential equation. This differential equation comes up in Green's functions a lot, at least when I was doing my homework, it did. So yeah, see how powerful this is. Frobenius solution failed. Cauchy Euler approach also did not give us a good approximation, but it did give us did not give us a good answer, but it did give us something to start with, the value 1, a constant, and this indeed worked. Now again, this again depend on the Wronskian. If the Wronskian was something else, we would have something bad, because you can then, because otherwise you could have argued that if you have 1 which will solve any differential equation all the time, a homogeneous differential equation, it will definitely solve, because all the derivatives will be 0. Then we would have a natural log solution, but that's not true because it depends on the Wronskian. A Wronskian had a good form here. See, that's how powerful this Wronskian is. So I hope you see the benefits of using this method, although it's it doesn't seem like much if you just look at the definition a priori, but it's a lot. It's a beautiful method when used in conjunction with other methods like this. So that's it for this video. I think I talked too much today. Please like and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Diagram in the math community. And in the meantime, stay home, stay safe, keep doing math, and peace out for more content. Next video, I'm going to talk about the Wronskian approach again, but for non-homogeneous linear differential equations with a driving term, not just 0. So it's going to be a little more interesting. See you next time.